Hi guys, welcome to HSC Chemistry and the acidic environment video series. This one we're going to have a quick look at buffers. Now buffer solutions are ones that are going to bring a few of the different concepts that we've looked at so far together. So the important thing to know about buffer solutions are buffers are solutions which control changes in pH in response to small additions of either an acid or base. So the point of a buffer is to maintain a reasonably constant pH of a solution. And this is achieved by having equal mixtures of concentrations of a weak acid and its conjugate base. One example of a weak acid that we've looked at before is the carbonic acid molecule. Now this carbonic acid, when it's in water, so if we put this into water, then what will happen is we'll put it as an equilibrium, actually long way this way, will form the HCO3 minus ion in aqueous solution and the hydronium ion as it donates a proton to the water molecule. And this is what we get left behind. So this is the acid, and what's left behind once that proton has gone is called the conjugate base. A buffer solution is simply when the concentration of this, concentration of X, okay, is the same for both the acid and its conjugate base. And because we know that this is a weak acid, it will not fully ionize. So one of the ways of making a buffer solution is to have not only the weak acid, but also a salt, such as, say, sodium bicarbonate or sodium hydrogen carbonate, that we add to the solution in order to increase the concentration of the conjugate base. So we get to a point where both of these two values are equal. What will then happen, or how we explain the function of a buffer, is then in terms of the shift in equilibrium. So if an acid is added to the buffer, then what we want to do is reduce the concentration of hydrogen ions. So if we go back to that equilibrium we just looked at before, I'll remove the subscripts just for the purpose of discussion. So here is the equation, remembering that we have equal concentrations of the acid and the conjugate base. So what happens is if we add an acid, we're going to increase the concentration of the H+ ions. That's what an acid does. So that's the change that we've made. So that is the change. So the Le Chatelier effect will be to shift the equilibrium to the left. So when we shift the equilibrium to the left, the concentration of both of the products will decrease, and the concentration, well, not of water, but certainly of the acid will increase. And so this is according to Le Chatelier's principle, that when we make a change in the system will shift in order to counter that change. The same is the case if in this case what we change is the addition of a base, add base. What the base will do is it will reduce the concentration of the H3O+ ion. So that will be the change. The Le Chat effect will be to shift the equilibrium to the right. In this case, what we are doing is we're decreasing the concentration of the acid, but we will be increasing the concentration of the conjugate base because we will be increasing the concentration of the hydronium ions to counteract the drop. So buffer solutions can be explained in the same way that we've been explaining any Le Chatelier shift in the equilibrium system. And this is designed to help to counteract the effect of either the addition of an acid or a base in order to try and shift the system to maintain a consistent pH value. So this is the net effect, that the pH solution containing the buffer remains fairly constant. Now, if we were to add a very large amount of a very strong acid, we would shift the pH. A buffer solution will remain within narrow range, but can't resist all changes. Buffers are very important in some natural systems, and it's important to make sure that you have one or two of these that you can use to explain buffers in natural systems. One of the important buffers in living cells is the one that occurs between the dihydrogen phosphate and the hydrogen phosphate ions as a conjugate acid-base pair. The key thing here, of course, is if this is acting as an acid, so this particular species, then the equilibrium exists between the H plus ion and the HPO42 minus ion. So this is the acid and this is the conjugate base here. And of course we know that this is actually going to be represented by a hydronium ion, but it's just for simplicity's sake that we know that this is where this particular equilibrium lies. And this helps cells maintain a pH value of around about 7.2. The blood is also important, and we've talked about the hydrogen carbonate ion, and it too is useful in helping to maintain consistent pH values for things like seawater and also human blood, sitting in around about a 7 to 7.4 kind of a reading. Thanks for watching.